Professor, I think you're on mute.
You totally right. Sorry. Thank you very much for that. Sorry. And I had just given away all the answers to the exam. No, okay, thank you. I said nothing. Okay. Yes, thank you. More people coming. Okay. So yes, hello, Maisha. Good afternoon, Mark. And if that was Mark, thank you for that pointing out. Good afternoon, Athea. Hi, Leslie. Good afternoon, Manoj. Good afternoon, Ruby. Oh, that was my, thank you, Maisha. Good afternoon, Zimin. Good afternoon, Weishi. Good afternoon, Lisa. Good afternoon, Alyssa. Good afternoon, Nick. Hi, Catherine. I'm fine, thanks. How are you? Yeah, and I'm muted. Thank you, Leslie. Right. Okay. Hello. Good afternoon, Andrew. Good. Hello, Alona. Hi, Michaela. Hello and good afternoon, Jessica. Good afternoon, Jaylyn. Good afternoon, Catherine. Hi and good afternoon, and to everyone, Lizzie, if I may say. Cool. Oh, and more people. Okay, okay. And a lot of videos, which is awesome. Wait, sorry. I know there's someone else trying to get in. I think there is. Oh, maybe. No. Okay. I think that's everyone. I think that's everyone. Okay. We're going to get straight. Yes. Okay. So I totally see. Yes. So hello again, and Jessica and Weishi and Lizzie and Mark and Manoj and Zimin and John and Althea and Leslie and Ruby and Maisha and Lisa and Catherine. Yes. Hello. Oh, the directions. Wait. Yeah. Oh, yes. Yeah. Okay. So we're going to get straight to exam stuff right now. So let me, okay, I'll start by trying to answer Weishi's question in the chat. The directions in the practice, and so Weishi is doing the right thing by looking at the practice exam. It's all about the practice exam from here on in. If you have the document with you or electronically, like, you please do have it out in some way. The directions in the practice exam do say to justify all answers in order to receive full credit. And yeah, how you justify your answer. So this is answering Weishi's question in the chat. Yes, the more you can write explaining how you got your answer, the better. Like, and I'm going to try to show you that again today. Like any solutions I give you is my attempt to show you an example of what you would want to give me. The more, in this case of an exam, the more you give me to explain thought processes, the better. Let me try to make, so number one, the real exam, which will be posted Wednesday evening, I'll get to that again in a second, will look remarkably like the practice exam. Certainly the directions will be the same. The equation sheet will be the same. The format will be the same. So, I mean, so Weishi is totally right to take anything that's in the practice exam as a serious indication of what to worry about. Like, that's correct to do that. And yes, your job in the real exam, what you're really trying to do in the real exam is you're really trying to show me that you understand why the answers are the answers. That is what you're trying to do in the exam. There's a million ways to do that in a way. And the more you really understand why the answers are the answers, the more you'll see how your exam really can look different from your neighbor's exam, from your colleague's exam. Like, it's like anything else in life. The more you actually get it, then the more you can say it your way. Now, and I'll try to be more detailed about that today. But one concrete version of justifying your answers is to do the 5-step method that we've been trying to say here, and that I'll repeat again today. Like, and you can, so by the 5-step method, I mean, someone's entering, hold on a second. And I can write that again. I can write it again. I can write it down. In fact, let me just very quickly, I'll jot it down right now, just in case there's any ambiguity. But by the 5-step problem solving method, what I mean, excuse me, is not, and more people are coming, hold on. But I'll say this right now. I'm going to, so here we are today. I'm just going to. But in particular today and in class Wednesday, which we will have, and I'll say more about that in a second, it's pretty important that today and Wednesday, like if I start saying anything, you guys really can, in the, like right now, I want to answer Wishi's question because I think it's in some ways probably on everybody's mind. So right now I'm going to quickly jot down here what the 5, I'm not going to make a whole explanation. We're going to just quickly remind you right here what I mean by the 5-step problem solving method. And as that's as a guide, like when in doubt, every time you're solving any problem on this exam, make sure you've done these 5 steps. Like think of it as a checklist. You can even provide them to, you can even label your work this way as you go, if you wish. You don't have to label your work this way, but you sort of do have to, you know, cover this. It's almost like a rubric for grading. When I'm saying, but I'm also saying if all of you right now in your hearts are like, yes, he's said this 50 times, like I know the 5-step problem solving method already, like, oh my God, like you could write in the private chat, right now, like, please move on to something else. And I won't be insulted. I mean, I have to make a judgment call if everybody says that or not, but like this is your time for me to try to give as much pointers as I can, as many pointers as I can about the exam for today and Wednesday. Now, I think it might benefit a lot of you for me to remind you of this. I'm going to try to say it quickly. But again, of course, this is in old videos and old notes and all of that. Okay. Now I'm going to say, like from early classes, from the beginning of the semester, if you look back in your notes, there's at least one video, and it's titled. There's like one video, like how to do homework or something like that. You could play it again, and in detail, I explain what all these 5 things are. I'll say it really quickly now. Obviously, I don't want to waste everybody's time and go through a whole class on this right now. But this is a good checklist for you to bear in mind as you're trying to solve things for me on the exam. You want to kind of make sure that you've done all of these things pretty much every time. Like, so I'm just going to say it quickly again for reference, but I would recommend that you go back and look at the videos. But the first thing is diagram and fact pattern. Like for any major problem, make a diagram first. Present the facts in your own words. Like and again, you'll see me do this in a minute, but diagram and fact pattern. Then what is the question? Like again, to all of you, even though I know that you know that I know the question, it doesn't matter. In your work, in your blank paper blue books, you're making it clear to me every step of the way. If there's any doubt in your mind, make it clear to me. The question is like, what is the velocity or whatever? So that's WI. So first you like, here's the facts, here's a diagram of the situation. Then here's the question. By the way, say you've done this all for like part A of problem 1, and now you're on to part B, right? Now you're on to part B, which is clearly a different question, but probably refers to the same diagram and fact pattern as part A. Certainly in part B, you can just write something like for diagram and fact, see above. You can do that. You can use common sense and reasonability, but just make sure you've consciously addressed every one of the items on this checklist. And again, you can even put in a different color next to what you're doing. You can like check these things off. It'll make it easier for me to read. But anyway, so first is diagram and fact pattern. Then what is the question? Then general definition and principles, right? So if I'm asking what is the velocity, even if you think you can do it in one step in your brain, which maybe you can, even if you're like, I can totally get the velocity, still take a moment to write down like average velocity triple equals sign displacement over time. Like write the concept of average velocity, right? For credit, to show that you understand what's going on. Then step 4 is PAW, particular application and work. Like, so if I were asking if I'm like the displacement is 3, the velocity, if I were like the displacement is 3, the time is 2 seconds. I'll say it again. If I were like the displacement is 3 meters, the time is 2 seconds. literally, like that may seem like a one moment thing in your brain, but if you do this carefully, you will have drawn a diagram of that. You'll have written the facts down. Displacement equals 3 meters, time equals 2 seconds. Then you'll write down like V average equals question mark. Like you'll make it clear to me what the question is. Then you'll write down something like average velocity, triple displacement over time. Like you're writing down the definition or the equation, if you like, or the law, whatever it is. Then you're applying my numbers and you're writing like here, average velocity double equals sign 3 over 2, you're 3 meters over 2 seconds, and you're dividing, and then you're getting a final answer, which is average velocity, V with a bar over it, double equals sign 1.5 meters per second. And you're circling that. That's what step 5 is, final answer circled. Okay, so this is just a basic skeleton of like 5 steps that pretty much should be addressed every single time you're solving a problem, even if in some of the cases of some of these steps, you're saying like refer to above or refer to last page or something like that, right? So it's a long answer to Wishi's question, and I'm going to go back to the exam in a moment. Well, I'm going to answer questions all period. I mean, any questions you have about the exam is what I'm here to do. Oh, cool. Thank you. Oh, great. Okay, great. Okay, thank you. That's really helpful. And that's points, blah, 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 for closing conversation. Let me say to everybody now too, the reason I just took a while on that, the reason that was like a very valid question is please understand that when you turn in the document to me next Monday, and we're going to get to that in a second also, when you turn the document into me, it is understood that you will have been allowed and encouraged to do anything you want from Wednesday this evening when the thing gets posted. Okay, so here we go with logistics. All the logistics about this, hopefully you found in your Google stream this morning, like just kind of like, it says something like expectations regarding midterm exam. It's just like the clear rules and procedures, whatever. It will be posted this Wednesday evening, no later than the ending of lab period. And lab, I'm not saying that you necessarily have lab, but people have lab until 8:30. In fact, actually, if someone in the chat, if you're following me, if someone in the chat could just remind me when you guys do have lab, I would love to know. I am vaguely planning on it. I mean, you're not the only section taking this, but if someone could just remind me in the chat when, oh, today, 4:30. Okay, thank you. That's awesome. Okay. So your exam, thank you. And that's points, blah, blah, blah. Your exam will be posted no later than 8:30 Wednesday evening. It might get posted a little bit earlier. If it does, that's not to alarm you. That's just because I'm just saying I'll post it whenever I have it ready up until 8:30 p.m. Then you guys all do. Oh, and let me back up a step further too. Thanks to Mark, I believe it was Mark, and I really appreciate it. He pointed out the glitch in the schedule. We will have class Wednesday. Like I won't, like just because I feel like you deserve it, we need it. We will have normal class at 3:05 Wednesday where I'll continue to answer any kind of concerns or questions about the exam, where I'll continue to address anything in the practice exam. Like I won't do any new material Wednesday. It'll still be an attempt to help you with this exam. So we will have a real class. I'm going to, from today and then, I'm going to give you as many more solutions as I possibly can, but you're not going to have answers to every single thing in the practice exam. You're going to have, a sampling of answers and solutions to the practice exam as best as I can give it to you. Maybe I might email you more, but I'm not promising that. So some things you're really going to have to work out on your own, and some things you'll have guides to work out. But once we have our last class on Wednesday afternoon, then a couple hours from then, the actual exam will be posted in Google Classroom. It will look like it'll look like homework, but for 100 points, and it'll say exam on it. From that time, you have until 3:05 the following Monday to do whatever you want to figure out this exam. That certainly includes looking at any solutions I gave you to the practice. That certainly includes going back to the practice. That certainly includes going over your notes. Certainly includes rewatching any videos or notes that I posted, which I highly recommend for the last few classes, like the last 3 weeks. Like sometimes you have class, sometimes you have a video, same thing with the other section. Please do check out all the, everything I've said over the last 3 weeks is somehow very relevant to this exam. If you're going to watch anything, watch that stuff. And to be honest, even when 2 videos have a very similar title, like even when I do something for both of the classes, slightly different things happen in slightly different sections. So at least scroll around and see if I address something that you're interested in. But anyway, you can do anything you want from Wednesday evening to Monday morning, you can and should talk to one another. I'm saying even when the exam has been posted, you can work. Oh yeah, you already know this. We already talked about this. Okay. So, but I mean it. You're going to talk to each other. You're going to do whatever you want to figure out this material. But then by the time Monday comes, you're writing out on your own blank pieces of paper your solutions with your name on it. You are not footnoting anything or citing anything. You don't have to tell me that I went to Khan Academy. You don't have to tell me that I got this equation from my friend Sam or whatever. Like, of course, no one's expecting that any of us made up physics. It's understood that you can use as many resources as you want. But here's the catch, just to make this, I just want to be as clear as possible at this. By Monday, what you're writing is the fullest explanation you can of everything that you now by Monday understand, right? Ideally, you might have even tried some rough drafts or some scratch work on papers and checked it out with your friends or whatever. But by Monday, whatever you're writing down things that you understand. And your goal by the time you get to Monday, and I will move on in a second. I know I've said this 100 times to some of you, but remember that I know that you know the answers. Like the answers, some of them I will have given to you already. Some of them your friends are giving to you. Some of them are on the web. You're not there to show me the correct answers. I know them. You're there to show me that you understand why the correct answers are the correct answers. Your exam is like a proof in that sense. You're proving why the exact answers are the answers, and you're proving why it actually makes sense to you. So that's really your goal in the exam, is to show me that you get it by now. You're not trying to prove that you always got it. You're trying to prove that you get it now. I mean, by the time you hand it in. And to that end, and this is the last, right? And I think everybody knows in their hearts what I'm saying, and I will grade them accordingly. And you all know that the more you understand a particular problem, once you have that aha moment, and it may not have happened for some of you yet, but there's still plenty of time for it to happen. I mean, for each one of these problems, if you look at them now, and I'm going to turn to it in a second, I'm sounding intense again as always, but we're going to turn to the exam in a second. And I'm going to tell you that I think it looks intimidating. Whenever I open a physics question for the first time, especially an exam, it always looks very thick. Even to me, it always looks like, oh my God, like what is going on? Like there's a lot here and I don't even know if I know this stuff, like what's going on. But if you go step by step and break it down, especially if you have help of solutions sitting in front of you, you'll see that things start to fall into place and start making sense. That is the magic of physics, that everything looks absurd when you first look at it. And then you look at it enough and it starts looking so obvious after a while that you don't even understand why it's a question anymore. Like that happens to all of us. And you know that this happens to all of you because almost every one of you in this room, once you get something, you always get very apologetic and overly polite to me. Like, you're like, can you explain this? And then I explain it. And then you go, oh yeah, okay, got it. Right? Everybody always does that. Everybody's like, oh, I'm a total idiot. Oh yeah, okay. Because you do feel that way once, but it's not true. You're not an idiot. It's just the nature of physics that it's like sense falling into place. And whenever sense falls into place, we all retroactively think that we weren't being sensible. That's just not true. It's just stuff that's falling. So your goal is to make this fall into place by Monday. And here's the logistical thing of that. The one thing that I'm strict about, I just got to be very clear, and you can replay this video. I am strict about the timing of exams and appearance. By 3:05 of Monday, when it's due, at that moment, you do have to turn it in. It's the one thing I am strict about. You do have to get the exam in on time, and then you have to show up to class. You can fade out of class, like you can turn off your video and like you could fade out after 20 minutes if your brain is overloaded. And it won't be a hard class. I can tell you that right now, it won't, but you have to be there to show your classmates that you're there and that you turned in your exam. Anybody who's missing from class, like at 3:15, looks to everybody else like they're still working on their exam. And guess what? They probably are, right? And then it looks to everybody else like I'm going to just be okay with that because I'm okay with a lot of things, but I'm not. I need you to know you don't want to be that one who's just missing from class at 3:05, still all of a sudden scrambling out answers, because then all your colleagues will feel that you actually let them down at the last minute, right? Yeah, no, I know. Wait. Well, I'll tell you right now, on Starnisha's thing, honestly, the best thing I could say about Starnisha wrote in in the chat, and I am glad we're talking about this. She wrote, oh, time restrictions. Why not midnight maybe for the final? Here's the thing. Time restrictions are very scary for me too. It's almost why I have to get it out there right now and say this. Okay, I'm very weird about time. I mean, you know what they say, if you can't do, teach. And if you can't manage space or time, teach physics. They don't actually say that, but they should. I'm very weird about time too. And I'll tell you right now, to cut to the chase, with your final, yeah, your final probably will be due at midnight. Your final exam, it probably will be due at midnight and it will be due at the end of finals week. It's going to be just like this, where it's take home and all of that. It won't be due the day that technically you have a physics final. You will have probably till midnight with the final. But with this, I can't do it that way, because the one thing, I want you all to work together, and I don't want, like, my one belief is that the only thing that's actually cheating is if one person in the room gets away with something that everybody else like didn't get away with. So the one thing with this is, with this midterm exam, you do have to turn in on time, and then you have to show up to class and be there so that your colleagues don't think that you are taking an unfair advantage. Especially imagine if like a bunch of you work together and you all work together, and then like 3 out of 4 of you like stay up all night to get it all together, and then you like bleary-eyedly show up to the class, and then the one of you is like still dancing around doing it, and then the rest of you are thinking, oh my God, they're totally taking advantage of, like, now Yavram's totally going to let them get away with that because he's such a pushover, which I generally am, and like that's totally unfair because we all killed us. If we had known we could have gotten away with that, we would have too. So I'm saying to everybody right now, that's one thing you can't. You got to show up to class at 3:05. Your exam has to be in. I might even do that thing, you know, when I say hello to everybody, like, I don't think I'm going to embarrass anybody or call anybody up, but when I say hello to you on 3:05, I'm like, that's me congratulating, acknowledging, well done. You've already done the hardest part of this thing in a way, which was putting it to bed and showing up for real. And I'm telling you all right now, am I a human being? Yes. Are you guys human beings? Yes. Do things happen in life? Yes. So if something happens to you in life, and I mean this very seriously, I have learned this from both sides of the following human equation. Once this thing gets posted Wednesday night, and again, I'm encouraging you all to work together. I'm encouraging you to not compete and to try to optimize one another's understanding and optimize one another's grades. And I'm reminding you that if you all get an A legitimately, then that's a good thing. It's not a bad thing. Okay, so but therefore, if God forbid, if electron forbid, if one of you has a situation between Wednesday and Monday, something in your family, something with COVID, something emotional or psychological, if you start having a situation where you know, whoa, physics is not the only thing in my life, I'm not going to be able to get this thing in on Monday, just text me. In fact, I keep forgetting. I'm not saying there aren't exceptions. I'm not saying that physics is the only thing in your life. I'm not saying that things can't arise. Things might arise. Just text me and tell me that something is arising, and be realistic with me and like be polite and respectful. But if on Friday I get a text from one of you that says, I can't get into the details now, but there's a family event, or I can't get into details, but something is happening in my life, can I please, I cannot turn the exam in 3:05. Can I please tune it in Tuesday at 3:05 or Wednesday at 3? Just give me a concrete counter proposal. Tell me that there are circumstances. You don't have to tell me what they are if they're personal. I'm not saying that. And you certainly don't have to prove them. What you do have to do is just give me a heads up. As long as you can find the 1 minute to manage your time and budget your time to communicate with me and not surprise me, then that's cool. That will happen. Don't be that person every time. I mean, this is going to be our first exam together. Then we're going to have a final exam, then a 2-3, then hopefully quark willing, electron willing, we're all together again for the same type of routines in 204. Use your judgment. You know that I don't care what the reasons. It's not my business. I just care about patterns. If you're the same person every single time, never being able to make an exam in on time, then we've got an issue and we've got to talk. But you know if you're not that person. So, okay, so I don't want to spend any more time. So what I'm saying is this, I'm totally rigid about the timing. The exam does have to be in on time Monday at 3:05, and you have to show up to class unless you can't, in which case, just communicate with me and we'll work out an individual circumstance. And we will. I will work it out with you as long as you keep me posted and you communicate and you give me a realistic expectation. Like, I'm not going to have it by Monday, but I can have it by Thursday, whatever. Okay. So I'm just going to pause right. And you should do it by text, not by email, because then we'll do it faster. Oh, yes. Okay. Yes, exactly. Direct chat person. That's exactly what I am going to do. As a matter of fact, yes. Okay. And I was going to ask everybody if that was clear what I just said. Actually, I'm going to move now to the actual thing. But can anybody besides direct chat person just confirm in the chat, is what I'm saying clear about timing and communication, all that? What? Clear. Okay, cool. Good enough for me. Okay. So now, cool. All right. Thank you. Okay. I'm going to go now. Right now, I'm going to open the exam. I've got some, and again, you could stop me at any time as I'm talking. You could ask me other questions of the exam, but I'm going to try to maximize your time here. But I want to solve now what I think is actually, in a way, the hardest part of the exam. I'm going to solve it for you now, and I'm going to try to show you while I'm doing it how it relates to other parts of the exam as well. Okay, so I'm intentionally skipping. I'm going to and also, I'm going to try to do it a little bit differently from what I did in the other section. So between the two videos, you can get a lot, hopefully. Okay, so what I'm going to say is, here's the part, like everything in this exam you in principle can solve right now with the equations you have, but of course some is easier to do with practice than others. So I'm going to split the screen for a second. I'm going to go to, I'll show you. Well, okay, first, what's on the front screen right now is a mathematical way of saying Galileo's principle of relativity. Okay, I get really into this I got really into this into the other section this morning. So again, if you want to expand the discussion of this, you can play the video from this morning. But let me just say in short right now, what's been happening in this class that is really important, but might be confusing to some of you at this stage, it would be confusing to me, is we kind of have two threads going in parallel. We have all these equations and mathematical like problem solving techniques that are happening and that ultimately are sort of what we get tested on. But then we've got this other thread that I keep in English talking about Galileo's principle of relativity. I keep talking about the nature of velocity, the character of motion, and how like the earth moves even though we don't feel it. And I keep saying that Galileo's principle is a principle that can be stated many, many different ways. And each of those different ways that it can be stated is, I call a form. And what I've been trying to argue is that each new way of saying it is slightly more advanced than the old way. They're all part of the same idea, but each new way of saying the principle gets us more and more help in actually solving these mathematical problems. Now, it might not seem that way to you quite yet, because it might seem like there's math over here, and then there's like this English philosophy principle over here, and they might not seem that related to you. What I have here on the board here today is the next step of really linking that English to the math. What I'm really trying to say is the more you really understand Galileo's principle, the much easier the math is to do, the much easier it is to solve these problems that look very mathematical. In fact, let me say even more specifically, what often happens to people, especially when they're having their first exam in physics, what it feels like to a lot of people a lot of the time is, okay, I can do the physics once you get me started. Yeah, like once you show me the equations and you set up the problem and you start it, then I know how to run the equations and do the physics. But what I often don't know is how to start. I often don't know really what the question means, or I don't know which equation to use first, or I don't know how to set up the problem. Once I've set up, then I can do it and I can follow what you're saying and it makes sense. But I can't really do it on my own because I don't really know how to start. That's what people say a lot. And it's a reasonable thing to think for a while. Let me tell you guys two things. One, if you don't know how to start a problem, that's where the 5-step method comes in really important into play. But two, a lot of the times the way to set up a problem, the way to choose what equations to use or how to is actually to really understand Galileo's principle of relativity, because it tells you to make certain choices, like choose your reference frame, choose your coordinate system, label your axes, things like this. So, but to really link, so the more you can really study and the other videos or the other notes and really look at what I mean by Galileo's principle, what I really mean to say that velocity is always a relation between two objects. It's never just a property of one object. The more you really will see how to set up problems. But now let me be more concrete and tell you, and I'm going to relate this to the exam, like I promise, like 1 minute. What this is for, right? What's here on the board right here is form number 4 of Galileo's principle. We've had 3 forms, then we even had a form that we called 3.5. Here's where it really starts looking mathematical. It may, I don't know if it looks like gibberish or if it looks obvious to you, but here's what it's saying. pick any, and again, I'm going to relate this to the hard problems in the exam in like 1 minute. It's trying to say, picture any 3 random objects in the world, any 3 that have 3 distinct constant velocities, like object A, an object B, and an object C. 3 random objects, A, B, and C, that each have a different but constant velocity, okay? What this is saying is, if you really take the principle of relativity seriously, it's saying velocity, and I'm writing V every time in here, these are all V's, but the arrows above the V, the arrow is like a little vector arrow, and it's trying to denote that we really mean velocity as a vector here. I don't just mean speed, I mean velocity, magnitude, and direction. Like all these statements are about magnitude and directions of velocities. The first statement says VAA triple equal sign 0, meaning if you ever just have one object A, I don't care what object it is, but if it's just one object and you ask, what's its velocity? Not compared to anything else, but just like compared to itself, just what is its velocity? You're always going to get 0. The velocity of my hand relative to itself is 0. My hand is always with my hand. You see what I'm saying, right? What's the velocity of Earth? I could say, oh, you mean relative to the sun? But if you say, no, just like actually, what's the velocity actually of Earth, like in and of itself, relative to itself? The answer is 0. Earth is not moving away from itself. So the first way is just a way of saying you always need more than one object if you're going to discuss velocity meaningfully at all. But then the second part on the sheet says VAB always equals negative sign VBA. That's, I don't know if it's clear enough, but that's supposed to be a negative sign right there. Hold on. And what that means is, okay, you need 2 objects to really discuss a velocity meaningfully. You can't just have one. But once you have 2, velocity is always a symmetric relationship, always symmetric. So if I say that the Earth is going 65,000 miles an hour to the west past the sun, to the east past the sun, then the sun is going 65,000 miles an hour to the west past the Earth. It's always reciprocal. If I'm going 40 miles an hour northeast relative to you, then you're going 40 miles an hour southwest relative to me. And which one of us is actually right? Both of us, or for that matter, neither, right? Velocity is a relation. It's a symmetric relation. Either holder of the relationship is equally correct. So it's just a matter of what you pick as a comparison. Then finally, and here's where I'm going to relate to the exam now, the part that's hopefully almost just as obvious as the other 2, but much more powerful is, okay, now, what if we have 3 objects? Like if you have 1 object, velocity is meaningless. If you have 2 objects, velocity is meaningful, but it's like almost too straightforward to tell us anything. It's just like symmetric. If you have 3 objects now, what this last statement says is velocities add as vectors. Velocities add and give you results. Now, how do they add? Like vector, like they add. You can add velocities, and that's what we're going to do in the last problem of the exam. You can add velocities in the manner of vectors, just like we can add displacement velocity, just like we can add displacement vectors, and just like we did in the class last week. In this class, we remember somewhat quickly, and we were finishing it right as class was over, but then there's a video posted of it, and the video is called Adding 2D Displacement Vectors, or Addition of 2D Displacement Vectors. Important video, and it'll help you a lot for this. It's just showing you how you add 2 quantities that have magnitude and direction, even when they're in 2 dimensions, even when direction now involves not just up and down or not just side to side, but both at the same time. And the whole trick of how we did that, of how we added displacement vectors, was we broke each vector up into its components. We treated each diagonal arrow as a sideways arrow plus an up and down arrow. And we like independently tabulated what was going on in the XY world, and we independently tabulated what was going on in the X world, and we independently tabulated what was going on in the Y world. In other words, we used SOHCAHTOA and Pythagorean theorem to break up every 2-dimensional displacement into 2 one-dimensional displacements that were occurring simultaneously yet independently. That's what we did like last week We took displacement vectors. We took one like this and one like this, and we got a total displacement. We found out how far up and over we ended up if we first went over and then we went like in some random direction. We added up the components of those displacement vectors to get a total displacement. What I'm here to say now, and again, we're going to do this concretely in a minute. I'm just trying to give you the overview, especially if we do get cut off or anything. I'm saying velocities are also vectors. They add exactly the same mathematical way as displacement vectors do. They add, or you can add them by adding up their components. Totally the same method. If you follow the method we did with displacements, it's going to be the same as with velocity vectors. The thing that makes it seem a little bit more exotic or a little bit more abstract or something is, what does it mean when we add velocity vectors? Like what are we figuring out about the physical world? And here's the deal. And then I'm going to move on. What this last statement is saying will make total sense to you if you just think of it in its most limiting sort of extreme or simplified or one-dimensional case. Like what this thing is saying is, pretend your objects, your three objects, A, B, and C, are me. Like pretend object A is me, pretend object B is the subway, and pretend object C is like New York City streets or a subway platform, a subway station, whatever. Those are the three objects: me, subway, and platform. Okay. What this last statement right here on the sheet is saying the velocity of me relative to the subway plus the velocity of the subway relative to the platform yields the velocity of me relative to the platform. Right? It's almost obvious, right? Like it is obvious in a way. I'm saying now that that's actually true in general, but let me say it again. Velocity of me relative to subway plus velocity of subway relative to platform yields equals totals up to velocity of me relative to platform. That's why I take subways, because I could be going 0 miles an hour relative to the subway, i.e. I could just be sitting in the, okay, now I look like I'm making a hip hop album, but like I could just be sitting, chilling in the subway, right? So I'm going 0, let's say, relative to the subway, i.e. I'm not moving seats. I'm not like I'm looking at a piece on the wall and it stays with my eyes the whole time. So I'm going 0 relative to the subway, while the subway goes 85 miles an hour relative to platforms, relative to the stations, relative to, you know, like Broadway Avenue or whatever, right? And so those two numbers add. 0 plus 85 gives me 85. And what is that? That's the velocity of me relative to the streets. So I get home, right? Like that's why I take the subway, because I could be doing nothing relative to it. But as long as it is doing something relative to something else, then I'm doing something relative to something else, right? It's so obvious you wouldn't even think it needs an equation to write down to say it. But why? Well, why that equation is meaningful and why we're going to actually use, or it's just another way of saying something we always knew, which is that velocities are relationships. But what that does for us, writing it down like that, and I'm going to show you this in the exam, is what that means is that's true in general. That's true even if none of the numbers is a 0, even if some of the numbers are negative, and even if things are going in cockamamie directions, like in 2 dimensions, it still holds true. Now, quick example again, like you know this, you know you can walk up the down escalator, right? You know the escalator could be going down at 25 miles an hour relative to the mall, and you could be going up the escalator, sorry, so the escalator could be going up at 25 miles an hour relative to the mall. And if you're going down at 25 miles an hour relative to the escalator, so if the escalator is doing positive 25 relative to the mall, and you're doing negative 25 relative to the escalator, negative 25 plus 25 makes 0. And you know, especially if you're a little kid, like my little kids used to do this, you could like be running down the up escalator, and if you adjust your speeds exactly right, your legs can be moving while your head stays at the same place in the mall. I think you all know what I'm talking about. That's just confirming that this statement is true. Velocities add like vectors, as long, and even when there's negative signs, like they can cancel themselves out, as long as we're bearing in mind the reference frame relationships, right? So, and it works even in 2 dimensions. That's what you're going to see in the problem that I'll do right now. Okay, and you can stop me again, but so that's like the overview of what's going on. It's just, but now I'm going to go to the problems. Let me Oh my gosh. Okay, I'm going to switch screens for a second to show you where I'm talking about. So bear with me for a second. I'm going to. Oh, sorry. Hold on one second. So I'm going to the practice exam now. And again, let me remind you, your actual exam will look very, very much like this practice exam. It won't be identical, but it'll be like extremely similar. So I promise it's not a trick going over this or something. Yeah. So, okay. So there it is. So why? Okay. Yeah. Okay. Again, stop me if I'm being confusing at all, or if I'm going too slow or too fast. But all right, here you okay. So the exam is now on the screen. What I'm going to do right now, we've got time. Okay. And I know, and again, I'm sorry if I sound all rushy and stuff. And it's just because I want to get you as much information. I mean, it's not meant to panic you. But all right, if you look on the screen right now, part 2, Galileo's principle of relativity. What I'm going to do right now in the interest of time with this problem, I'm going to tell you this problem absolutely tests the concept that I just said, the concept that velocity is a relation, not a property. What it really tests most of all is the first 2 little lines of that. If you saw on the board that there were 3 equations, right? Like VAA equals 0, VAB equals negative VBA, and then the last one, this really asks you to deploy the first 2 of those more than anything else. And a little bit, it asks you to deploy the third, but it's really asking about the first 2. Let me tell you that this problem right here, I'm going to say some things about right now. This is a one-dimensional problem. This doesn't even get into vectors or anything like that. This is a pure one-dimensional problem. And this problem is not easy. It's not easy, but it is simple. It's kind of like those hill figure problems and stuff we did at the beginning, where if you get it, then you get it. And you don't have to do a ton of mathematical work to do this. I'm going to give you some hints right now. If you don't get it, it's possible to do a whole ton of mathematical work and get yourself confused. Here's what I mean. First of all, I'm going to tell you the answer to this right now. Okay, you might want to jot this down. I'm going to tell you the answer, and I'm going to tell you a major hint of how to get that answer. But I'm not going to do the whole thing out for you. I'm going to let you think about it, at least for right now. And you can ask me more Wednesday. But first of all, well, the answer to this, well, yeah, I mean, what it's asking in this problem, it's giving you a couple of basic facts, and it's asking you to figure out how fast the water in this problem is moving relative to the shore. Okay, again, you can read it on your own. Well, here it is right there. I'm not going to read it out loud and everything, but it's giving you a couple of basic facts. I mean, you're in a boat, you're like traveling, there's water moving downstream. So water is moving relative to the shore. You're in a boat, you're going upstream relative to the water. You're like paddling it along at some constant speed that is unknown, some constant speed relative to the water. Okay. The water is going at some constant speed relative to the shore. Both of these are unknown, at least at the beginning of the problem. You're going upstream. As soon as you pass a bridge, you drop a bottle out of the boat, it says. The bridge is just kind of like a marker to make it clear to all of us like exactly where and when the problem begins. So right when you pass this bridge, you drop a bottle out of your boat, okay? And you keep going at your constant speed, at your constant unknown speed. You keep going. Now the bottle is in the water and starts then just gliding downstream. It's just traveling with the water. The bottle, that is, necessarily is in the same frame of reference as the water. If the bottle were to look over at a water molecule, the water molecule would stay with the bottle at 0 velocity, right? And if a water molecule were to look at the bottle would be sitting still relative to the water. And I'm not trying to trick you. I'm trying to make that clear. So the water and the bottle are just heading down, while you in the boat are going up at some speed relative to the water. Okay, first of all, what we have here is like 3 objects in effect, like A, B, and C. They happen to be like water, boat, shore. Like you could call them W, B, and S or something like that. Any of the statements that I just made on the front page would apply to these 3 objects. Okay, but I'm going to go further. You're going up, you go up, you keep paddling your boat, at a constant speed relative to the water. And then 20 minutes pass and you notice, oh no, we left the bottle. Oh, we don't have a bottle anymore. So you turn around the boat and you start going down. According to the problem, you go down at the same constant speed relative to the water as you were going before. I don't know what that speed is yet. In fact, I never do. But whatever it is, it's the same. Okay. So VW, excuse me, like VBW, velocity of boat relative to water, it is the same number as it was whether you were going up the water or down the water. Okay. And you start going down. If you're following me, if you're paying attention, you might realize that that means that someone standing on the shore would certainly see you coming down now a lot faster than you were going up, right? Because you were going against the current at some speed. Well, so while you were going up, the current was going down. It kind of is like walking up the down escalator, if you know what I'm saying. But then after 20 minutes, you're coming down. So now if someone on the shore were watching, they would watch someone go really slow relative to the shore, and then they would see someone going really fast relative to the shore. That's what someone on the shore would see. But someone in the water, someone just in the frame of reference of the water, like the bottle, would see you going up at a certain speed and then back down at that same speed. Like that's what the problem is saying. And you want to be able to, oh, good. Yeah, okay, yes. I'm glad. All right. I'm psyched for what Maisha is saying. I'm glad she did try to do it before. Right. And like all physics, in a way, what's really hardest about this is understanding like what the scenario is. Once you get it, so that's sort of maybe why I think it's worth it. I think, and Maisha can tell me or anybody else, I think it's worth me trying to break this down for you a little bit right now. And I think you'll find it a lot easier once I do, but I'm not sure. If Maisha's saying she's already good and everybody's already solid, I'm happy to move on, believe me. Yes means that this is okay. Yes means I should keep going, or wait, I should keep talking. Please. Okay. Cool. Thank you. All right. That's many points. Okay. So what I'm saying so far, so the scenario is that the boat went up at a given speed relative to the water. It now comes down at the same speed relative to the water. That is exactly as though you were in a subway. Let's say it's like you were in a subway and you're walking through the subway, and then you turn around and walk back through the subway to your original seat. And like, you're always moving your legs in the same muscular way. Like you're always expending the same amount of energy. And if you look down at the floor while you're walking, or you look at the seats, that you're passing the same number of people every second on your way up the car as on your way back down the car. But the fact is, but someone outside watching you, I mean, this is the whole thing of the relative nature of velocity. Someone outside watching you would see you first walking against the direction of the subway, and then they would see you walking with the direction of the subway. Or if you want to picture this on an escalator, and maybe it's even easier to picture it on an escalator, like you're first walking down and up. First, you're walking up an escalator that's moving down, then you're moving down the same escalator. So someone in the mall watching you would totally, to them, you'd be going slowly and then quickly. Right? I mean, I'm not trying to confuse anybody, but that's the point here. But anyway, that said, I'm looking at the chat again. Oh, okay, cool. Okay. All right. So so you do that so what happens is you're going up for 20 minutes, then you see that the bottle's dropped. So you start heading back down for the bottle. Then the other fact that's given in the problem, is by the time you reunite with the bottle, okay, and you do reunite with the bottle because you're paddling down the water now. The bottle is just floating along in the water. It's going at some speed relative to the shore, but you're racing, you're paddling downstream, and you eventually catch up with it a mile below the bridge, right? Because it's been going the whole time and you're going, so you catch up with it. And the question is asking, the question that's being asked is, all right, given these bare bones facts, how fast is the water going relative to the shore? Okay, that is like asking how fast is the subway or the escalator going relative to the mall. And we're claiming that you could figure that out from the facts that are given in the problem. Okay, now before anybody try, I'm going to say more about it, and I'm going to switch. It's not the only problem I'm going to solve today. I'm going to give you the skeleton of this, and then I'm going to solve something more mathematical in a second. Although, chat. Also, I'm also going to say, in the other class this morning, I focused more on trying to solve the last problem in the exam, which I still think I'm going to get to today. but I didn't focus as much on this. So again, if nothing else, just watch both videos and you'll have a full explanation of both problems. But what chat? Great question. So I'm getting something in the direct chat about the actual answer to this question. I'm going to say so with all due respect, and the person who's in direct chat totally gets a lot of points, plus 11 points for this. I'm going to say the answer that's put in the direct chat is not quite right. I will tell you right in 1 second. I'm going to tell you the actual answer to this. And I'm even going to basically show you how to get it, but I'm glad someone's asking. That's good. So I'm about to say the answer, but let me just make the question super clear before I say the answer. The question to everybody is, given these facts, given that you drop a bottle, paddle upstream at some constant speed relative to the water, and then you paddle downstream at the same speed relative to the water, and then you reunite with the bottle a mile below the bridge. The question is, how fast is the water? Yeah, totally. Direct chat person. Yes, please do. And LOL. Yes, please do that. But I'm psyched. The question here is, how fast is the water going relative to the shore? And before I even say that answer, because I don't want to confuse anybody, I will say the answer right now. I mean, I will. But before I say it, let me also reinforce. Notice there's a lot of things. This is very much like one of the questions from the beginning of the year, in that one thing you're not ever told is how fast the boat is going relative to the water. You are never told that. You are told that it's always the same number, whether you're going up or going down. Okay, and that means it's always the same number relative to the water. It definitely won't be the same number relative to the shore. If you're following what I'm saying, if you're thinking about the boat you're told is going one speed relative to the water up, then it goes the same speed relative to the water down. If you're following me and picturing this and really trying to understand it, you'll realize that someone standing on the shore they'll observe something different, and you're both correct. Someone standing on the shore would see someone going up slowly and someone coming down quickly, because they're observing from the shore, not from the water, right? But you're never told how fast that boat is going relative to the water. What I want you to notice is you're also never asked. You're not asked. Is it figure outable? Perhaps. But just like the problem at the beginning of the year with the Hill figure, since you're never told it and you're never asked, it seems pretty clear that you don't need it. I mean, you can get it, don't get me wrong, but I don't think you need that number in order to get how fast the water is going relative to the shore. Now, how fast is the water going relative to the shore? I'll tell you the answer right now so that you can check your own work or whatever. The answer does turn out to be very close to what someone in the direct chat put. But the answer to how fast the water is going relative to the shore is 1.5 miles per hour. I'm just going to say that. The answer to this question is 1.5 miles per hour. One of the reasons I'm saying it right now is, even if you get this exact problem in your exam, if you just write 1.5 miles per hour, that's not full credit. To go back to Wishi's, question in the chat, you're going to have to show me why that is. Now I'm going to tell you, right? And this is one you're really going to have to think through. Once you get it, you'll definitely get it. And then you want to spend all your time showing me that you get it. But until you get it, you might feel like you don't get it. So you have to debate it with other people and stuff like that. Here's the trick for this problem. If you try to solve this problem always from the perspective of the shore, if you try to make all your diagrams and all your numbers crunching from someone standing on the shore, you can solve it and you can get the right answer, but it's going to take you a really long time, and you're going to very possibly continue to confuse and frustrate yourself, because to someone on the shore, it will perpetually seem like we don't have enough information. It will seem that way. It'll seem like we have a boat that's going up really slowly and then down really quickly. It'll also seem, through a perspective of someone on the shore, it'll seem like we've got a boat that's going up some amount of time for 20 minutes in some distance, and then coming down much longer and unknown distance. It'll seem like there's all these unknowns if you're observing this from the frame of reference of someone on the shore. But the major insight of this problem is, if you really take Galileo seriously, if you're looking at this and you're like, exactly like Maisha said, like, oh my God, the theory of this seems so confusing. Like, I don't even know where to begin. Here's where to begin: is be the bottle, like literally, or be the water. I'm saying, if you really get the concept of Galileo, you'll make your math much easier. The math of this is actually quite straightforward and quite short if you solve this problem from the perspective of the water. What the heck do I mean by that? And again, I'm not going to give the whole thing right now, and you can ask more questions on Wednesday. But because I want to also get to another problem, I'm just going to do the skeleton of this right now. But I'm saying if you look at it, and you really might have to let this sink in or talk about it with yourselves. But if you look at this, if you really believe that all perspectives are equally valid, like to the earth, I'm sitting still right now, but to the sun, I'm moving through the space at 65,000 miles an hour. They're both correct. It's just a matter of what are you comparing me to, right? Or to a subway, I'm going 0 miles an hour, but to the New York City streets, I'm going 85 miles an hour. They're both correct. It's just a matter of what are you comparing? Like all velocities are comparisons. So if you really take that seriously and you look at this problem, comparing everything to the bottle or to the water, which is the same thing, like the bottle is in the water, it's just floating along, right? It's just sitting still. Then from the perspective of the water, the boat is going up at some speed for 20 minutes, right? And then it's coming back down at the same speed. It says in the problem, the boat goes up at some speed relative to the water and some constant speed and comes back down at the same speed relative to the water. Okay, what does that mean? That means if you're a water molecule and you think you're still, right? Because you are always still relative to you. I mean, it's just like playing life like one big video game. If you're a water molecule, like if you're a water molecule, or if you're the bottle, same thing, because the bottle is just like floating along next to a water molecule, right? They're both sitting still relative to each other. If you're the bottle watching the world, and stay with me on this. Again, I'm actually giving you much more of an explanation now than I did this morning. So again, you might have to watch the video for the other problem, but watch this carefully now. Think about this carefully. If you're a bottle in the water watching the world, what are you going to see? First of all, you're going to see a bridge going up. Excuse me. Sorry, no, you're not. You're going to see a bridge going down away from you, right? Because sorry, I just said it wrong again. If you're the bottle in the water, right, you're floating down below the bridge. So first of all, you're going to see a bridge rising up from you, right? You're going to see the shore and land and everything going up because you're coming down relative to it, right? And you're not wrong or right. It's just what you're observing from your frame of reference. You're going to see the bridge and the land and everything going up. You're also going to see a boat going up, right, away from you. Like if you're that bottle and you just dropped up. By the way, if you go on YouTube, I've had students in the past make all kinds of videos simulating exactly this problem, and they're on my YouTube channel somewhere, or they're referred to somewhere on. I mean, you can play simulations of this if it helps. But from all the different frames of reference, but if you're sitting there, the bottle, and you're watching, you'll see a bridge going up away from you, right? From the moment you get separated from that bridge, you'll also see a boat going up away from you. And if you're thinking this through properly, you'll see the boat going up faster than the bridge, right? Because it's going up at some speed. So you'll see a bridge going up away from you. You'll see a boat going up away from you. The boat will go away from you for 20 minutes. Then it'll turn around and start coming back to you. Now, here's the key point for problem solving. I'll look in the chat in 1 second. Well, I'll look in the chat 1 second. Oh, cool. Oh, great. Oh, great. Perfect. Yes. Good. Thank you. So I'm so glad. So I seem a little less crazy now. Well, I feel a little less. Yeah. It's all about imagining you're the bottle. You just heard it straight from a tutor. Yes. Imagine you're the bottle. And that's the key of the whole problem. And again, it's not really imagine. I mean, it is imagining, but this is not fairyland. Like it's legitimate physics. If you imagine you're the bottle, you'll see the bridge going up away from you. You'll see the boat going up above that bridge, right? And here's the key point. In 20 minutes, that boat's going to change its mind and start coming back down to you, right? Like that's what the problem says. In 20 minutes, the boat's like, oh, crap, we have to go get this bottle now. So it'll start coming back down to you. Here's the thing. Relative to you, it's going to come back at the same speed that it was going up. Like not relative to someone on the shore. To someone on the shore, this is a very hard problem. It's not impossible, but it's very hard because the boat's going to start coming down faster now to someone on the shore. But to you, being the bottle, it says in the problem that the boat is moving at the same speed relative to the water down as it was going up. And by the way, is that possible? Yeah, it's totally possible. Just like you walking back and forth along a subway or along an airplane, like if you have to go to the bathroom, like you don't adjust your speed according to the 500, right? You just do your thing. You walk to the bathroom and you walk back. If someone were outside the airplane looking in, watching you as you pass over continents, they would see your motion be kind of funky. But to you in the airplane, it's just there and back. Constant speeds, same thing here. So the boat goes up at a constant speed relative to you for 20 minutes. Then it turns around and starts coming back to you at the same speed. Now think about this. This is going to bother some of you, what I'm about to say. It's going to bother some of you because it's going to seem too easy. It's going to seem like a cheat, but it's not a cheat. It's physics technique. What I'm going to say is this. If you are the bottle and you're watching the boat go out, 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 out for 20 minutes, and then in a very short amount of time, turn around and come back at the same speed back to you. It went out at one speed. It's coming back at the same speed, and it's coming back to you. It went out some distance. I don't know what that distance is, but it's now coming back the same distance relative to you, right? If you're a water molecule or if you're a bottle, this is very important. Please note that I'm yelling, not because I'm angry, but because this is such a subtle point. To you in the water, not to someone on the shore. Someone on the shore, this is going to look crazy, like up and then down a long way or something. But to you in the water, the boat to you, the bottle, the boat leaves you, and then it comes back to you. So to you, the boat does a round trip, some distance out, same distance back in, right? And apparently it does it at some speed out, same speed back in. So here's the key thing, and then I'm going to look at the chat. I actually am, you're going to have to write this down, but I'm telling you, this is the solution to the problem. I just don't want to confuse anybody. I'm literally vocally solving the problem for you right now, but you'll prove to me that you understand the solution once you write it out and give me diagrams or give me whatever. I'm saying from the perspective of the water, the boat goes out for 20 minutes and then comes back the same distance at the same speed. Why the same speed? Because the problem says. Why the same distance? Because it's from an object back to that same object. It's a round trip. Relative to the water, it's a round trip. The boat leaves the bottle, and now it's going to come back to the bottle. And right, so it's this one distance out, one distance back. Same speed out, same speed back. Therefore, what's my point? My key point is, if it took 20 minutes to go out, it must take 20 minutes to come back to the bottle. That's hugely important. I'm saying that this entire round trip must have taken 40 minutes. I'm going to look in the chat in a second, but as long as I'm spending this much time explaining it, and again, the other problems explained more rigorously in the other video, and plus we could also do it tomorrow. But as long as I'm spending as much time, I want to make it as clear as I can. I'm saying what you can easily know if you observe this problem from the perspective of the bottle, but you cannot easily know. You can know it, but not easily. If you try to solve this perspective, if you look at this problem from the perspective of the shore, you're going to think a lot of things that are right, but are going to confuse you and not help you in the end. If you think of it from the perspective of the bottle, what you see is a boat go out for 20 minutes and come back to the bottle in another 20 minutes. You'll see that the in trip must be 20 minutes because the in trip to the bottle must be the same distance and must be the same speed as the out trip. Now, and that means we're almost done solving the problem. We're just about done. The key thing was realizing that the out trip is 20 minutes, the in trip must also be 20 minutes. You might say to yourself, wait a minute, doesn't the bottle, I mean, you might say to yourself, wait, the boat on the way up only goes like up to point B. And then by the time it reaches the bottle, it goes all the way back to the bridge and all the way further down. So you might say, doesn't the boat have to go this like really, really far trip? Yeah, from the perspective of the shore, it does. But that entire extra bit that the boat has to do, the bottle also does. So the bottle doesn't care about that. The bottle just watches a boat go out and then come back into the bottle. The entire time, the bottle watches the shore zooming up while it's happening, right? Just picture yourself in an airplane with things happening within the airplane while you see the clouds or the continental United States like fly past you. That doesn't affect what's happening inside the airplane. Physics is physics is physics, right? So I'm saying if you're the bottle, and I'm just about done, again, just because I made the choice to dive in this, I'm diving as deeply as I can. If I'm the bottle, I see a boat go away from me for 20 minutes. I see a boat come back to me 20 minutes later while the bridge and the shorelines continue to go up. Well, that's the last bit of information is the bottle went out for 20 minutes, came back 20 minutes. So the bottle's been in motion for 40 minutes. During that time, the bridge went up away from me. How far did the bridge go up away from me if I'm the bottle? Well, apparently 1 mile, it says in the problem, right? I mean, the problem says that the bottle ended up a mile below the bridge when it was reunited with the boat. That's the same thing as saying that the bridge ended up a mile above the bottle when the bottle was reunited with the boat, right? This is all just relativity, all that first page that I showed you a couple minutes ago. So what I'm saying is the bridge traveled a mile away from the bottle, or the bridge traveled a mile up from the water, or put another way, the water traveled a mile below the bridge in the 40 minutes that this whole round trip occurred. The water traveled 1 mile in 40 minutes. In other words, it traveled 1 mile in 2/3 of an hour. 1 divided by 2/3 is 3/2, 1.5. Like the whole problem is the water traveled 1 mile in 40 minutes past the shore. Therefore, the water is traveling 1.5 miles per hour relative to the shore. End of story. Let me say, it's that simple. It's totally what Maisha said at the beginning. This is all about really understanding physics theory. If you really get the physics concepts, the math is 3 lines. The math is 3 lines. The answer is 1.5 miles an hour. But you can see, I think, some of you right now are like, oh, and some of you are like, what? I mean, I don't know who's who, I'm not saying I know who's who, but like, once you get it, it's almost annoyingly simple. But until you get it, it's annoyingly complex. I am telling you, that's why I can give you an exam where I can tell you the answers and still call it an exam. Your job is to go away from me from this and think about it with your friends and really see that you get it. One way to see that you get it is try it also in the frame of reference of the shore. You could still get it in the frame of reference of the shore. You could get it a lot easier now that you know what the answer is, but you'll hit a lot more complexities and you'll have to do a lot more equations. It'll still all work out. Physics is physics. The answer is one. I'm not saying the only way to see this is to be the bottle, but I'm saying that gives you a huge advantage over the math, and that's what physics is really about. So the answer to this is 1.5 miles per hour. The technique is solve the equations from the standpoint of the bottle, i.e. deploy Galileo's principle of relativity. And we're going to do, and all that's going to happen in the harder problem that I'm now going to turn to, I know I only have 7 minutes, and it's okay, I'll continue it on Wednesday and you can watch the video, but I'm saying, what you can see of this problem is the math is not what's hard to anybody. It's setting it up and doing the concepts. And the concepts are largely that velocity is relative. I mean, that is the concept. But the answer is 1.5. That's awesome. All right. I'll totally take what I'll totally take what Maisha is saying. So I hope that does. So that's one problem right there. And it's going to be on your exam. And just the more once you look, and then you know in your hearts whether you get what I'm saying or not. And if you get it, then go to town and just show it to me as deeply and personally as you can. Use different colors, use pictures. Show me, just like when I yell and scream about these things, show me what the misconceptions are. Say like, you would think that blah, 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 if you do it this way, but no, but blah, blah, blah. Like just go to town. Once you get that, you get it. Don't think, well, it's too easy. Show me that you, right? But if you know in your heart you don't quite get it, hash this out with your colleagues and talk about it a lot and argue until you do. It is about true intellectual honesty, not about chug honesty. Okay, let me go to the other one. Yeah, please. Jessica, great question. Please, yes, you could definitely use different colors. You could do think of this as like, it's like a report. You're trying to show me, like, make a diorama out of it. It's whatever. Like, it's trying to take advanced college physics concepts and reduce them to 3rd grade portrayal. Yes, definitely you can use different colored pens. You don't have to, but definitely you certainly can. Yes. Wait. Okay. Thank you. All right. Now I'm going to quickly go. And then again, if I get cut off at the end of this period, remember the other video, like from this morning's class, will emphasize more the other problem that I'm going to talk about now. So, and they didn't get this whole explanation that I just gave you. So I mean, everybody's getting something different, but you can just watch the videos and put them together. So now I'm going to go. I'll show you what problem I'm going to now. And I know all these look hard until you sit down and do them step by step, but do them step by step, and they seem easier as you go. This one here, honestly, I think this one, you can see on the screen, yeah, the free float, and I know we have 5 minutes. Okay, this one, I'm going to switch screens in a second. This one is very much like what we just did, okay? It really is. It's the same concept as what we just did, only now it's in 2 dimensions. Now things are going north and south as well as east and west. The key thing behind this is physics is physics is physics. The laws of physics hold in this axis, and they simultaneously but independently hold in this axis. So anything that looks 2-dimensional, you just break it down into 2 one-dimensional situations and just do the physics separately by SOHCAHTOA and by Pythagorean theorem, kind of like we did in class last week with displacements. But I'll show you what I mean. So I'm going to switch screens right now. And again, right when 4:20 occurs, of course, you all have other class, you leave. I will just stay and answer any questions. So you can leave and I won't be insulted, but I'll still be here for a minute. So don't panic. And we'll continue this on Wednesday, but I'm just switching to share. Okay, so now I'm doing, oh, thank you. Okay, well, I don't think it's over yet, but okay, yes, you have a good day too. Sorry. Okay, but I think we do have 4 minutes. Okay, but yeah, cool. All right, so here's this problem. Okay, so I'm doing the part 4 thing, free float. Again, I think it's the hardest one. So if you can really do this, you could do everything. And I'm gonna, so here's like my diagram and fact pattern. I'm just like here. So we have this river with water floating, and we have this boat that's going somehow like southeast relative to the water. And I give the facts. Relative to the water, it says the boat moves at 12 meters per second at 30 degrees southeast. Relative to the riverbank, the boat moves at 10 meters per second at 45 degrees north, north something, I forget, northwest, I think. So again, this is just like subways and whatever, like so we have like 3 objects here. Again, we have like boat, water, and riverbank or shore, same thing. And the boat can have one velocity relative to the water, but then the water can have a velocity relative to the shore. And so the boats relative to the shore would be boat to water plus water to shore, just like we were saying before, but in 2 dimensions. Okay, so I've drawn that diagram. Now I'm continuing to set up my diagrams and my facts here. I'm a student solving the problem here, right? I'm still doing like number 1, diagram and fact patterns. So I draw these little vectors, these arrows to represent velocities, like VB, like I say in the middle of the page, let R equal the riverbank, let B stand for boat, let W stand for water. I have a little compass at the bottom right that says like from here on in, anything that's going north will be called positive, anything that goes south will be called negative, and at the same time, independent of that, anything that's going east will be called positive, anything that's going west is negative. So from here on in, positives and negatives are just like the beginning of the year, what we deal with to deal with the 2 different directions on a given axis. But when we have more than one axis happening at the same time, we've got angles to precisely connote direction. So the velocity of the boat relative to the water is given at 12 meters per second, 30 degrees southeast. That means like south of an imaginary dotted reference line that's pointing east. Like southeast means south of east. Northwest means north of west. So then that other velocity vector that's given, these are just me diagramming the givens. Velocity of boat relative to water is 10 meters per second at 45 degrees northwest, right? So those are my givens. Now, and again, I am watching the clock. And again, we will continue this Wednesday, but again, you can also watch the other video. It now starts asking me questions. The first, just like Maisha said before, this all might seem really intimidating unless you take it step by step and realize it's more strict. It's not trying to trick you. So the first question that the thing asks with 1 minute left, it says, what's the direction of the water relative to the boat? That's what it's asking. What's the direction of the water relative to the boat? How the heck could I possibly know that? Well, I know it because what was given was the velocity of the boat relative to the water. And this is just that thing of relativity. I am to you the opposite of what you are to me. If the boat is going 12 meters per second southeast relative to the water, then the water is going 12 meters per second at 30 degrees northwest to the boat. That's the answer. All it was asking for in the first question was direction. So the answer is 30 degrees northwest. That's the answer. You see, I'm going fast, but it's just saying relativity. Then the next question is, how fast is the river going to the boat? Well, the boat, we were told the boat is going 10 meters per second relative to the river. So the answer still has to be 10. If I'm going 10 to the east relative to you, then you're going 10 to the west relative to me. That's all it's asking me. It's 4:20. Obviously, you have to go. I'm going to say like one more quick thing here, just summarize what happens next in the hardest part of the problem, and then I'm done, but we'll pick up on Wednesday. C asks, what's the water doing to itself? Like, what is the water relative to the water? The answer is 0, always. Anything to itself is 0. So we're just sort of doing exercises here to set things up until D, where D is the real issue of the problem. I will really get it. I will do this all out for you Wednesday if you want. But D asks, what is the boat doing? It asks, what is the water doing relative to the riverbank? It's very much like the problem we all just talked about a minute ago. It's asking what's the current in the water, given all the facts that we have. And it's in 2 dimensions now. So the way to get that is literally the A, B, B, C, A, C thing that I put on the page at the beginning of this. Again, if you have to go. I'm just about done. I'm sorry to go over time. I just want to try to wrap this up for you. I'm saying A, B, and C could stand for any objects. Say they are boat, water, and riverbank. Then what's just like with subways, have a good day. Thank you. Yes, have a good day. I appreciate it. Then you could, as long as the letters are set up in the correct order. Yes, goodbye. Yeah, go. If you have to go, I'm going to finish my sentence for my own sake, but go. No insult, no woman, no cry, no foul. Thank you. Well, actually, let me even see if anybody is here. Finish my sentence. Okay. Yeah. Okay. Bye. I'm going to finish the sentence just for anybody who's still here. But I'm saying VAB plus B, in general, for any 3 objects, A, B, and C, VAB plus VBC always equals VAC, right? Always, whatever they are. And it's obvious in the easy cases, like me standing on an escalator, but the whole point of the physics is that it's true even in the hard cases, even when there's negative signs involved. Have a good day. Yes. Even when there's negative signs, even when there's 2 dimensions involved, that relationship is still true. So I'm using that relationship here. I'm going to say the velocity of the relative to the water plus the velocity of the water relative to the riverbank must equal the velocity of the boat relative to the riverbank. That's what I'm writing here for D. That's my general principle right there. It's GPR form 4, right? And then I'm noticing, what the problem's asking for, what it's actually asking for is the velocity of the water relative to the riverbank. It's all the other information has been given. So I just rearrange this and say, VWR equals VBR minus VBW. Where did I get that? I just subtracted VBW from both sides because it's like math. The math works now. The math isn't the hard part. The hard part is setting it up physics-wise. So I have that. So all I'm going to do now, and I'm going to pause, I know we all have to go, but all I have to do now is subtract one vector from the other. How do I do that? Just like we did in class with displacements last week. I'm just going to take each one. I'm not going to hold you here now, but I'm going to take each one of these arrows and divide them into components. I'm going to get an X side and a Y side, like from SOHCAHTOA, so I'm going to say like VWX equals 12 times cosine of 30. And I'm going to say like VWY equals 12 times sine of 30. And I'm just going to put those numbers in the chart and add or subtract those numbers up and get an X total and a Y total and put them together into one big Pythagorean triangle to get the final answer. I'm not going to do it now because I know everybody has to go, but I will do it Wednesday, especially if you remind me. But that's the procedure. It's just adding vectors, just like we did last week, only it's velocity vectors. Okay, so that's, thank you. Okay, great. Thank you, Mark. That's good enough for me. All right, so that's again, let it all sink in, but it's as hard as it gets, really. Thank you, guys. I'll see you Wednesday. You are the best. Thank you. I'm still here just in case there are questions. I mean, I'll go. Yes,
Professor?
yes.
Oh, so